All right, the final speaker of the session is Omar Hafez. He is completing his PhD at the University of California at Davis, and his field of research is computational solid mechanics under the supervision of Professor Mark Rashid. Omar stayed within the Bay Area for both of his practicums, spending the summers of 2013 and 2014 at Lawrence Livermore National Lab.
Okay, so since I've already been introduced, I'll just go ahead and get started. Title again, just real quick. Toward automating patient-specific stress analysis from medical imaging. Just a short story. In 2009, I tore my ACL. I was misdiagnosed. I didn't get the surgery until 6 months after I had originally damaged my knee. In that period of time, I developed cartilage damage behind my kneecap. This is an MRI after the reconstruction. There's a hole drilled in my bones to replace my ACL. As you can imagine, from a mechanics perspective, that's going to change the mechanics of my knee. Fast forward in 2015 now, I've had 4 surgeries on this knee, ACL reconstruction, arthroscopy, microfracture, cartilage transplant, meniscus repair, and here on the right, you see this is a slice looking down on my knee in an axial view, and this is my patella, and this is some cartilage damage. And in trying to understand why my knee degraded so quickly, I realized there was much to be desired in terms of analysis techniques used by doctors and radiologists from a solid mechanics perspective. So I decided to be a champion of change, and so the basic idea is we have medical imaging in the form of MRI or CT, and on the right we have physics-based simulation, solid mechanics, and the idea is to combine these two technologies. Just one more quick anecdote. I was shadowing a surgeon a couple years ago, and he was walking me through an arthroscopy that he was doing on an older patient, and he was kind of talking about what he was doing, and he's looking in, and this patient has about 3 or 4 major defects in his knee. And he told me, I don't know which one's causing him pain, so I'm going to try to fix one of them, and if it doesn't work, then I'll have him come back and I'll do a total knee replacement on him. So that's the kind of thing that I want to try to change that mentality and try to have a little bit more science and prediction involved. So here's that pipeline. You start from medical imaging. You want to get down to any sort of clinical application. You have to segment the image, which involves essentially tagging every voxel in your 3-dimensional image, whatever material it may be. You want to define a boundary representation of those objects, which from an engineering perspective would be a CAD model. From there, you can produce an analysis-ready mesh, run simulations, and then make decisions. From a topical breadth perspective, it covers a lot of different things: image processing, computational geometry, finite elements, biomechanics. There's a lot going on. So just quickly talk about medical imaging for those who aren't, specifically MRI for those who aren't familiar. MRI measures weighted proton density of each point or voxel in a 3-dimensional field. And and from a clinical perspective, you get a set of 2D slices that represent 3-dimensional data. So if any of you have seen a surgeon or a radiologist looking through an MRI, they essentially scroll through with their mouse wheel the 2D slices and visualize in their mind's eye what's going on. So this is sagittal slices looking from left to right on my left knee. Image resolution for clinical applications right now is around 0.5 millimeter by 0.5 millimeter by 3 millimeters. There are 3-dimensional MRIs out there. There are higher resolution MRIs out there, but from a clinical perspective, not quite yet. The takeaway is essentially MRI provides 3-dimensional point intensity data. So in trying to get involved with this field, actually at this conference, I heard a talk from Fred Streitz about a pretty cool project involving simulating the heart using high-performance computing techniques. And so while I was in Livermore in my first practicum, I got in touch with the people working on this project, and last summer for my second practicum, I worked with the cardioid guys. And so it's a joint venture between Lawrence Livermore and IBM. I'm sure most of you are familiar with Sequoia and its capabilities. The project basically combines the electrophysiology and the mechanics of the human heart to do an unprecedented exploration of the mechanisms of cardiac arrest. And the reason why it's unprecedented is because of the high resolution, because of the high performance computing. Briefly about the mechanics, they modeled passive cardiac tissue as hyperelastic, incompressible material with orthotropic properties. They dealt with incompressibility with mixed pressure displacement finite elements. So you have balanced linear momentum and you have no volume change. Muscle also has an active stress, which is generated as a result of lengthening, but also velocity of the muscle fibers. And you have some ODEs that describe that. So you put those together, you end up with some differential algebraic equations. You linearize, and you end up with a large system of equations that you need to solve. They're using some novel iterative solvers to do so. So last summer I got involved. I was actually working on a canine heart. So this is the left atrium, and this is the right atrium, or the ventricles, my apologies. And you can imagine just facing your furry friend. And so you start with the medical imaging, your MRI, and you produce your segmentation. You color all of those voxels, which involves a whole slew of steps and tools. You extract a boundary representation, a surface mesh. From there, you can produce an analysis-ready volume mesh. This data is coming from Johns Hopkins, by the way. Continuing on, we generated muscle fiber orientations, assigned boundary conditions, ran results, and it was pretty good. It was pretty fun, and we ended up with some pretty cool videos at the end of it, simulating a beating. This is a canine heart. The project that the ultimate goal of the project is for a human heart, but all of a sudden now, speeding up this process of this tool chain, you can start answering a lot of questions that you can't answer before. You can ask what is the effect of over smoothing or under smoothing. You can do convergence studies. You can see how that iterative solver is sensitive to different mesh resolutions. So a whole range of sensitivity studies are all of a sudden allowed because of this improved pipeline. So now we can associate some pictures with this pipeline now. That being said, there was a lot of room for improvement. Image segmentation is usually done manually or semi-manually. The mesh generation can be cumbersome. That involves several different pieces of software, each with their own user-defined parameters. And ultimately, if we want to improve those, it may influence our analysis techniques as well. So I'll focus on mesh generation for the next couple slides. So our research group in Davis, we have a tool that provides a robust and topologically correct volume mesh if you provide it with a CAD model or a boundary representation. And so that's usually, from an engineering perspective, that's where the bottleneck is. That's where most of the time is spent in an analysis tool chain, is with meshing. So to be able to do that quickly is important and robustly. And so let's say we start off with this boundary representation. We create a bounding hex mesh, and then we sculpt the hex mesh with that boundary representation. And it's quite robust. It largely only uses integer logic as opposed to floating point operations. And what ends up happening is, through this routine, we'll look at one slice here. You end up with interior elements are just run-of-the-mill hex elements, and near the boundary, you end up with arbitrary polyhedral elements. So I'll focus more in on those. And for those of you familiar with finite elements have certain topological restrictions on there are elements that would not allow for this. So, so just in comparison, before I continue with that idea, the mesh that I was showing you with the cardioid guys, before pushing it to high, large problems, we're doing a problem with 856,000 degrees of freedom. For a comparable polyhedral mesh, you're looking at an order of magnitude reduction. So there's some other comments I'll leave out for now, but so great, we have arbitrary polyhedral elements that can be produced from meshing very quickly. So we need to be able to handle that because conventional finite elements cannot handle that. So we have a method that allows for dealing with arbitrary polyhedral elements, which allows for fast, robust meshing, which makes it no longer a bottleneck. Essentially, we approximate the shape functions that come from finite elements. I'm going to have to breeze through this. It converges at the same rate for some benchmark problems. Enjoys the same. It's in some ways it's the best of both worlds between mesh-free methods and conventional finite elements. I'm going to talk a little bit about that bridge between image segmentation and mesh generation. Image segmentation and mesh generation and a boundary mesh have very different kinds of data. A segmented image is a list of voxel positions and material types. And an analysis-ready volume mesh or even a surface mesh of an object is a set of points and locations, their connectivities, facets, et cetera, et cetera. So they're very different types of data, and it's important to keep that in mind when trying to produce a bridge between that. So some goals are to minimize user interaction, produce an explicitly defined, facetized, watertight boundary representation, which is non-trivial. And we want it to be robust and reproducible for that automated purpose. For now, I'm going to assume that segmented image is an input to what we're trying to do here. So whether it comes from manual segmentation, level sets, etc., we'll just assume that as given. So just quickly here, let's say I have my segmented little island in an ocean here. It's pixelated. And what we're doing is let's look at a window in that image. And let's identify a disk that shares the same area and centroid of that window. Let's approximate that interface with a circular arc, and then match the area and centroid of these green pixels with the intersecting disk. And you end up with a nonlinear system in this distance d and the curvature of this arc. From there, you can get a discrete point direction pair. And from there, you can throw down Voronoi sites. So Voronoi partitions, I hope at least enough of you guys are familiar with that. It's just a way to partition a space given a pair of sites, or a set of sites. So I'll give you a quick demonstration and example. So here was our original island. We'll identify the different windows in which there are multiple materials. We can compute the discrete point directions for each window. And then throw down the site pairs. If we were to do a Voronoi partition only of the site pairs, then obviously it's a non-ideal mesh even for our partition element method. But if we throw some additional sites down, and then I'm not actually showing them, but this would be the resulting partition of that. So hiding even that, we end up with our labeling of our set. And so on the left, we had a segmented image where each voxel or pixel was colored, and on the right we have an explicitly defined boundary. So from a visualization perspective, they're pretty similar, but from an analysis perspective, it's critical to be able to define that difference. So that being said, we want the boundary to be as perfect as possible. So the boundary's clearly been improved. We want it to be a circle. There are some little hitches, and we have some ideas about how to improve that. So it's still, some things moving forward, but I'll just lastly talk quickly about some application areas. I think when it's all said and done, this technique has some potential to play important roles analytically and predictively in medical applications. You can imagine improving diagnosis and treatment, identifying causes of pathology, improving surgical design, planning, computer-assisted surgery, surgeon training. So once an automated, truly automated or nearly automated process is bolted down and it's patient-specific, we have time to run lots of simulations, right? If we could do it quickly, we can get lots of data, and there's nothing to stop us from running clinical trials via simulation. And you can only imagine the kind of things that would open up. In order to make that happen, some things that need to be bolted down would be describing material properties better, boundary conditions, UQ and VMV are going to play an important role. Obviously, if we ever want to get something to be real-time or close to real-time, high-performance computing is going to play an important role. But I can envision in our lifetime imagining clinical trials, clinical simulation trials in which we could say something to the effect of, with 95% confidence level, changing the drilling angle by 3% for an ACL graft reduces the average patellofemoral stress by 10 to 15%. So that's the kind of thing that I would like to strive towards. Lastly, just give a thank you to my advisor, Mark Rashid, some of his collaborators. The guys at Lawrence Livermore were fantastic. Their collaborators at IBM, Krell Institute, CSGF. With that, I'll take questions.